Welcome to my channel Genius Math Expert. Students, today I would like to discuss about a formula for number of reflexive relations on a set. First of all, we should recollect the definition of the reflexive relation. So what is the reflexive relation? R is a reflexive relation on a set A if and only if A comma A belongs to R for all A belongs to A. Means, so whatever the elements are taken from A, with respect to that element, every element has its own image that should be belongs on the R. Every element belongs in A, every element having its own image, that order pair should be belongs in R. For example, let me discuss a set. A is equal to set 1 comma 2. A is a small set is taken. A is equal to set 1 comma 2. R is reflexive on A. R is reflexive on A. Means that set contains compulsory 1 comma 1 and 2 comma 2. Compulsory these two order pairs are must. So along this only this reflexive relation is existing on A, or possibilities of along with 1 comma 1 2 comma 2, all these are we can discuss now. See, suppose actually A contains 1 comma 2. A cross A Cartesian product can contains 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2. It contains 4 order pairs. Now if it is a reflexive, or is reflexive on A means, so compulsory R can contains 1 comma 1, 2 comma 2, these two are must. Along with other possibilities are what? If no other possibility is there, so this also we can accept as a reflexive relation, or else, so 1 comma 1, 2 comma 2, along with can we take 1 comma 2? Yes, we can take 1 comma 2. This is also a reflexive relation on A. So or else we can take 1 comma 1, 2 comma 2. So along with these two, can we take 2 comma 1? Yes, 2 comma 1 also we can take. So along with this 1 comma 1, 2 comma 2, can we take this both 1 comma 2 and 2 comma 1? This is also a reflexive relation on A. So means what we are understanding from this, so if it is a reflexive on A means, so A contains 1 comma 2. So A is having the two elements 1 and 2. So every element has its own image, means 1 comma 1, 2 comma 2 must be. Along with that other elements may or may not be. May not be means this is the smallest reflexive relation. So and if it is containing all possibilities, it is the maximum possibilities. So it is a Cartesian product, at the same time it is what? A reflexive relation on A. It is the largest or biggest. So it is containing, so 4 possibilities. There is no other possibilities are occurring. Now here, if it is containing only 2 elements means we can write this, it is first possibility, like it is second possibility, it is third possibility, it is like fourth possibility, we can write, we can count. But bigger number of numbers are given. A contains 10 elements. So number of reflexive relations on A. Suppose A contains 100 elements. How many number of reflexive relations on A. In that case, it is impossible to count like this. So in that manner, we have to derive a formula for to calculate the number of reflexive relations on A. So once a time we can recollect that what is a reflexive relation means every element has its own image. So such type of relation we call as what reflexive relation. This is defined on the set. And now here let us discuss, suppose a generalized formula we can derive now. Suppose here A contains A is equal to contains n numbers are there, 1, 2, 3 and so on n. So A contains n elements are there. So number of reflexive relations, number of reflexive relations on A is equal to 2 power n square minus n. Now we can discuss how it is 2 power n square minus n. Now here let us consider a n by n square grid. Let us consider a n by n square grid. Suppose, so here column headings are first we can give 1, 2, 3, 4 and so on. It is what n. Similarly here also 1, 2, 3, 4 and so on. It is n. So column headings are given, row headings are given. Now here common element for this is 1 comma 1. It is 1 comma 2. It is 1 comma 3. It is 1 comma 4 and so on. It is 1 comma n. Similarly it is 2 comma 1. It is 2 comma 2. It is 2 comma 3. It is 2 comma 4 and so on. It is 2 comma n. Next it is 3 comma 1. It is 3 comma 2. It is 3 comma 3. It is 3 comma 4 and so on. It is 3 comma n. It is like 4 comma 1. It is 4 comma 2. 4 comma 3. 4 comma 4 and so on. It is 4 comma n. And so on. It is n comma 1, n comma 2, n comma 3, n comma 4 and so on. It is n comma n. So now it is like n by n square grid. It is containing n rows and it is containing n columns. Totally it is inside in it. It is containing total n square number of elements in it. It is containing n square number of elements containing in it. And now here in these elements are two categories we can divide. Now here if I take this, these elements are like principal diagonal elements. These are principal diagonal elements. The remaining are other than the principal diagonal elements. Here if it is R is a reflexive relation on A, means A containing what I said 1 to n elements. If A containing 1 to n elements means all these principal diagonal elements must be belongs to there. All these principal diagonal elements must be belongs to there. So all these how many elements are there here? 1, 2, 3, 4 and so on. It is n elements are there. It is like n by n square matrix. So like that it is principal diagonal is containing these n elements are there. These n elements has only one possibility. There is no other selection. So already these are, if it is R is a reflexive on A means all these are N already selected. So now we are selecting for the remaining elements. So these N elements are compulsory, must be in that set. Then only it is a reflexive on A. So based on that remaining, how many are there? Remaining elements selections we have to think. So remaining elements are, remaining elements are total n square other than the principal diagonal elements. Principal diagonal elements are n. So remaining elements are n square minus n. Remaining elements are n square minus n. And now here the remaining elements are not compulsory. May or may not be in that set. Who are compulsory? Principal diagonal elements are must be compulsory in that set. So the remaining elements are may or may not be. So that's why, so each of the other elements, each of the other elements has two possibilities. Each of the elements are two possibilities. So therefore total number of possibilities for remaining elements are 2 into each elements has two possibilities. So 2 into 2 can be repeated remaining number of elements of times. Remaining number of elements are n square minus n. So therefore this is nothing but what? 2 can be repeated n square minus n number of, so times n square minus n number of times. So this can be simplified form. 2 can be repeated n square minus n times. So it is nothing but 2 power n square minus n. Therefore the formula for number of reflexive relations on a set which is having n elements is 2 power n square minus n. For example, now we discussed about one, previously we discussed about one set. So that is that set is A containing two elements 1, 2. So we can check with that two elements with the generalized formula. What is the generalized formula? 2 power n square minus n. Means n is equal to 2. Means 2 power, if A containing, we'll check that formula is satisfying or not. We'll check once. Suppose n of A is equal to 2. Therefore, so number of reflexive relations is equal to 2 power 2 square minus 2. Means 2 power 4 minus 2 is how much? 2 square is nothing but 4. How many we got? 4 correct or not? Once we can count. Already first itself we written. Here 1. See here 4 ticks are right drawn here. So here it is 1, 2, 3, 4. Among this is the smallest. So like this we can count. Not only for these two, with the help of this formula, any higher number of numbers are given. With the help of this, we can calculate this. So total number of reflexive relations on a set which is containing n elements is 2 power n square minus n.